Okay, this is video 24.4. We're looking at Gauss's law with cylindrical symmetry. Now remember, Gauss's law says that if you have an imaginary surface, the amount of charge enclosed in that surface is proportional to the net electric flux through it. And in the last video, we looked at how that applied to situations with planar symmetry. Now we're going to look at systems with cylindrical symmetry. And cylindrical symmetry is a little bit easier to understand. It's like a cylinder. If you have a cylinder, you can move up and down along it, provided it's infinitely long, and nothing changes. You can also rotate about its axis of symmetry, and nothing will change either. So generally anything that looks like a cylinder is going to have cylindrical symmetry. And the basic thing we'll do is an infinite line of charge. The charge density is lambda. And we're going to find the field at a point P, a distance r away from the line of charge. Now because of the symmetry of this, we're going to pick a Gaussian surface that is a cylinder centered on the line of charge and having radius r. We'll also say that the cylinder has length lowercase l, and we'll also see that the amount of charge enclosed is equal to the charge density times L. Now the next thing we'll say is the electric field of this line of charge is going to point radially away from the line at all points. And that means the flux through the end caps, or the flux through the ends of the cylinder, is equal to 0. And also because there's cylindrical symmetry, the field is the same at all points on the curved edge of the cylinder, so the flux through the curved side is just equal to E integral dA, where E is the magnitude of the field, and integral dA is the area of the curved part of the cylinder. You can imagine unrolling that into a rectangle, which would have length L, or width L, and a length of 2 pi r. So the total flux is 2 pi rl times the electric field, and we set that equal to the enclosed charge, lambda L, divided by the permittivity. We also notice that L shows up in both sides of the equation, so we can divide by it, and then we can get an expression for the electric field, E equals lambda over 2 pi epsilon naught r, which was pretty easy. Now remember back to I think the last video in chapter 23, we derived that same expression by integrating along the line, and it was a huge pain. That was much easier, and that is why we like Gauss's law, is in situations like this. Now here's another example. This is problem 19 in your textbook. You've got a conducting cylindrical rod of length L and total charge plus Q is surrounded by a conducting cylindrical shell with charge minus 2Q. Find the electric field outside the shell. So what we have is essentially a charge distribution that looks like this. We have this outer shell that has charge minus 2Q, and I'm showing kind of a cross section, and then inside it you have a cylindrical rod that has charge plus Q, and we're saying it's length L, but L is going to be assumed to be very large. And we want to find the electric field outside the shell. So what we do is we draw our Gaussian surface as a cylinder, where that's R, that's L. And the electric field is going to point, well, in this case, probably radially inward. Yeah, it will point inward because we've got more negative charge inside than outside. But anyway, if you look at the enclosed charge, it's equal to lambda L. But remember, lambda is the linear charge density, so the total charge divided by the total length. So the total charge is minus 2q plus q divided by length L, all times little l, which is negative q little l over big L. And once again, because of the cylindrical symmetry, we can say that the total flux is equal to the area of the curved part of the cylinder times the electric field. Again, the flux through the ends of the cylinder is 0 because the field only goes radially outward. And Gauss's law says that's equal to the enclosed charge over epsilon 0, which means 2 pi RLE equals negative QL over epsilon 0. Now what that negative sign means is that the field actually points inward, so the flux ends up being negative. And if we solve for E, we get, oh wait, forgot a factor of big L there. We get 1 over 2 pi epsilon 0 times Q over R times L. Yeah, that's how we get. That's what it is. And that is the electric field outside the shell. So this is only good for R greater than the radius of the shell. So it's fairly straightforward. The geometry can be a bit tough. You really have to have good three-dimensional visualization skills for this. But once you get the idea, the math is actually very, very easy. And part B of this, find the distribution of charge on the shell. Now that sounds like a very open-ended question, but because the shell is a conductor, the charge is going to reside on the surface. And so we want to know, it's basically asking how much charge on the inner surface and how much on the outer surface. And so what we'll do for this, I'm going to draw the charge distribution. We have the central rod there, and then we have the shell here. Now there's plus Q on this. Actually, I'm going to draw that a bit bigger in diameter. There's plus Q in here. And we're going to start with the fact that the electric field is 0 inside a conductor. And so what I'll do is I'll draw a Gaussian surface inside the conducting shell. And that means the flux through this surface is 0. And if the flux through that surface is 0, that means the enclosed charge has to be equal to 0. And that means, because you've got plus Q on the inner conductor, that there has to be minus Q on the inside of the shell. That's quite useful. And that means, since there's a total of negative 2q on the shell, there is another negative q on the outside surface of the cylinder. So when you've got conductors, there's some clever things you can do, like, for instance, draw a Gaussian surface entirely in the conductor, and know that as long as that Gaussian surface is entirely in the conductor, the enclosed charge is 0, which is useful. Now the last thing, we're going to find the electric field between the conductors. So that means in the space in here. So there's our central conductor, and there's the shell, which I'm not going to draw exaggeratedly thick, with minus 2q on it. But I want to find the electric field inside. So I'm going to draw a Gaussian surface in there with radius little r. And what we have here is the fact that because the negative 2q is entirely outside that Gaussian surface, it has no effect on the electric field. The enclosed charge equals q, just plus q, and that means that this is basically just a line of charge. Same field as a line of charge. And so electric field equals 1 over 2 pi epsilon 0 times q over L times r. And that field is going to point outward like that. And then those field lines end on the negative charge on the inside surface, and there are other field lines outside pointing radially inward that end on the negative charge on the outside surface. Now, for tomorrow, you should work a question and a problem, question 6, and then problem 17. That's what I'm going to check. Next and last video will be how to apply this in situations with spherical symmetry.